In the previous video, we have discussed preification. We have discussed several issues concerned with workarounds. We have seen what we mean by metadata, right? And then we have started with constraints, right? How all in a UML diagram you can show the constraints. So this is an example or explanation of this diagram that is on the next slide. And we had seen this, right? So constraints are always specified in flower brackets. Generalization sets. We have seen these 4 keywords in order to indicate constraints on the generalization sets. These are the keywords that UML defines: disjoint, overlapping, complete, and incomplete. We started with constraints on links, right? Multiplicity is a constraint on the cardinality of a set. I told you cardinality of a set means the number of items that are there in the set, whereas multiplicity is talking of number of instances of one class related to number of instances of another class. So when you say 1 to 1, the constraint is you are putting a constraint saying there is only 1 to 1 connection. When you say 1 to many, that is again another constraint, right? So cardinality is number of items, but multiplicity is a constraint on the number of items that a set can contain, because when you say 1 to 1, it can have only one, right? So that is a constraint you're putting on the number of items in the set. Multiplicity for an association restricts the number of objects related to a given object. For an attribute, specifies the number of values that are possible for each instantiation of an attribute. Qualification also constrains an association. A qualifier attribute does not merely describe the links of an association, but is also significant in resolving the many objects at the association end. So qualification also is one kind of constraint because it reduces your many and multiplicity n to 1. You have seen it, how it reduces it to 1. So when you talk about constraints, even these could be like constraints and they are on the links. Earlier what we have seen is on the objects and generalization sets. Today what we are seeing is on the links. An association class implies a constraint. An association class is a class in every right. For example, it can have attributes and operations, participate in associations and participate in generalizations, right? So association class, class and association, which is also a class, right? That also implies as a constraint. But an association class has a constraint that an ordinary class does not. It derives identity from instances of related classes. An ordinary association presumes no particular order on the objects of many n, right? So when you're talking of normal regular association, it does not presume any order at the many association n. The constraint ordered indicates that the elements of the many association end have an explicit order that must be preserved. We have seen this, so that at the many multiplicity of the many association end, when you write the word ordered in brackets, it means that it has a particular sequence, like your bags and sequences. So this is an example of subset constraint between associations, right? So this is an example of subset constraint between associations. So what are you trying to do here? You have a class called person and a class called committee. What is the relationship between them? Person is the member of the committee. Person can be a chairperson of the committee, right? But what is the constraint? For him to be a chairperson, this chairperson should be a subset of member of, right? So what is the constraint? The chairperson should be a member of the committee for him to become the chairperson. So the constraint being indicated here is the subset. That is, only one person can be the chairperson of any number of committees. Any number of persons can be a member of any number of committees. That is the multiplicity you are talking of. This arrow is indicating the direction that chair of should be a member of, that is a subset, if he has to be the chairperson of the committee. So this is a constraint on the link, because this association what you are talking about is when you deal with objects, it becomes on links. Derived data. A derived element is a function of one or more elements which in turn may be derived, right? So there is some data you already have. From that you can derive some data that is known as derived data. The best example for that is if I know your date of birth and if I know today's date, I can derive your age, right? So that becomes derived data. Derived element is redundant because the other elements completely determine it. So you need not again define age by saying so and so, right? You can derive it. Ultimately, the derivation tree terminates with base elements, classes, associations, and attributes may be derived. The notation for a derived element is a slash in front of the element name. you should also show the constraint that determines the derivation. So what you can do to show that it is derived data, first thing you need to put is a slash and then tell how that is being derived through a constraint. So if you look at the example here, you have a class person, you have birth date, you have another class called current date. So here I'm putting a slash and then I say age, which means age can be derived. How am I going to derive? You're putting it in this constraint and showing it age equal to current data minus birth date. Right, so current date minus birth date, you get that particular information of derived data. Packages. A package is a group of elements, classes, associations, generalizations, and lesser packages with a common theme. It partitions a model, making it easier to understand and manage. Large applications may require several tiers of package. Packages form a tree with increasing abstraction toward the root, which is the application, the top level package. Shows the notation for a package is a box with a tab. The purpose of the tab is to suggest the enclosed contents like a tabbed folder. So you see the UML notation for a package is always this. So this tab they are talking about, it looks like the contents enclosed in this. So it lets you organize large models so that persons can more easily understand them, right? So this happens to be your package name and how you represent that in UML. Okay? Before you somewhere end this chapter, some tips for devising packages. You need to carefully delineate each package's scope. The precise boundaries of a package are a matter of judgment. Like other aspects of modeling, defining the scope of the package requires planning and organization, right? So what all things you're going to put inside that package, right? You need to make sure that the class and association names are unique within package and use consistent names across packages as much as possible. So whenever you're defining a package name, follow some general rules, and whatever classes and associations you have in a package, try to make them unique. Define each class in a single package. The defining package should show the class name, attributes, and operations. Other packages that refer to the class can use a class icon, a box that contains only the class name. This convention makes it easier to read the class models because a class is prominent in defining its package. Readers are not distracted by definitions that may be inconsistent or misled by forgetting a prior class definition. This convention also makes it easier to develop packages concurrently. So these are few of the things you need to, tips that you need to follow while devising packages, right? So packages, this is a UML notation. These are the few things that you need to keep in mind. Make packages cohesive. Associations and generalizations should normally appear in a single package, but classes can appear in multiple packages, helping to bind them. Try to limit appearances of classes in multiple packages. Typically, no more than 20 to 30% of classes should appear in multiple packages, right? So this is another tip when you're trying to make a package, right? So this is all for your chapter 4. It's quite an elaborate and vast chapter, but all the concepts that are there with respect to class modeling and advanced class modeling, you have to go with them thoroughly, because the UML notation is very important for us, even for your lab. Unless and until these concepts are clear, the class diagram that you draw in your UML lab thing, right, would not be clear to you. So revise these concepts thoroughly of chapter 4, right? Go ahead and then have a nice day. See you in the next class with the next chapter. Thank you.